Now let's apply the concepts of entropy and mutual information to Gaussian random variables. So now S and N are both Gaussian. They have zero mean and standard deviation sigma S and sigma N respectively. In other words, the variance of S is sigma S squared and the variance of N is sigma N squared. And when O is equal to S plus N, signal plus noise, for example. And now because S and N are continuous variables now, the original formula to get the probability for O has to be changed from a summation to an integral. And now let's fill in the details. We get this Gaussian integral over S. It's easy to calculate this Gaussian integral, and so this is the result. It is a Gaussian distribution of O, and this O also has zero mean because both S and N have zero means. And it has a standard deviation sigma O, or it has a variance of sigma O squared. And this variance is equal to the summation of the variances from signal S and noise S. And this means that when you add Gaussian variables, you still get another Gaussian variable as an outcome. And when the variables are independent of each other, the variances add together to get the variance of the outcome variable. This is an important result you should feel comfortable with and familiar with. Now let's calculate the entropy of our Gaussian variable S, and this entropy formula is now an integral. We'll fill in the details and note how each of the two log terms arises from filling in the Gaussian distribution for PS into the argument for log 2. And we continue to the next step. The first two terms arise from integrating a normalized probability distribution times a constant. The third term comes from calculating the logarithm, and we transformed log base 2 to log base e. So it's natural logarithm, so that it's easier to calculate the log of an exponential. Continue to the next step. The first two terms copy down, and the third term comes from the definition of the variance of S. We come to the result. The entropy of a Gaussian random variable is equal to the log of its standard deviation plus a constant. We see that the larger the standard deviation, the larger is the entropy. This is quite natural. When the standard deviation is larger, we are more uncertain of the random variable, and therefore the entropy should be larger. Let's recall that when we have a random discrete variable A with n possibilities, n possible values, its entropy is log of n, when these n possibilities are equally likely. Now we can compare with the entropy of the Gaussian. The n possibilities for a discrete random variable becomes the standard deviation for a Gaussian variable. So they are, have related concept. So we can easily relate them to each other. That helps us to understand this. And now we can calculate the mutual information. And we write it in this form to make it easier. Since the conditional entropy of O given S is the same as the entropy of the noise. And now we can apply the entropy of Gaussian variables. Each Gaussian contributes its own standard deviation. One is sigma O and the other is sigma N. Now let's put in our knowledge that the variance for O equals to the summation of variances from S and N, so that we can write this results in another useful form, and this is in terms of the ratio between the signal variance and noise variance. And this is often called signal to noise, and we will often use this form later. If we change variables so that we define a new variable s prime as 2 times s, this can happen, for example, when we change measurement units, such as changing from measuring the length of something in terms of inches to measuring it by centimeters. So, expanding from s to s prime by a factor of 2 will also expand the standard deviation by the same factor. We end up making the entropy larger by 1 more bit. Imagine that you expand from 256 numbers to 512 numbers. It would also make the entropy larger by 1 more bit. So entropy value changes with a change of measurement unit. However, when you change unit like that, you have to change the unit also for the noise n, and also for the outcome O. So consequently, the mutual information does not change. Therefore, mutual information is very useful. Unlike entropy, it does not depend on the units we use to measure quantities.